This is a plan view of our distribution system. As you can see, this is the source up here. This is about 918 feet. The slow sand filter will be located right next to the source, and then the tank is at an elevation of about 850 feet. Goes all the way down to the river in a zigzag path because this is the path that they're actually going to have to follow to do the trenching. This is right where it crosses the river. That's where the pipe will be steel. And then here is the town itself. Each pink circle represents a house. We tried to maximize looping, although the town is kind of linear. But along the road, that's where the cover will be 24 inches minimum. And looping was done to ensure that if there's ever any problems in the pipe and maintenance needs to be done, there are other routes that water can be received. This is a profile view from the source to the highest house. Right here is the river crossing, this slope here. As you can see, there's a bit of a jump right before the river. And then it reaches the other side and travels up and slope to the highest house. This is a list of all the pipes. There are 121 pipes in the system, and we size them using an iterative process with WaterCAD, judging worst case scenarios, concentrating all the demand at a high end, at some of the more remote ends of the system, and as well as a balanced demand, just to ensure that all of our design criteria, pressures and velocities would be met regardless of where the demand is throughout the system. This is another plan view. It shows where we're going to be placing valves in our system. We neglected valves in the minor loss calculations because, as you can see, there aren't very many. The orange stars represent air and vacuum release valves, and they're at high points in the system. This blue star represents a blow-off valve at the lowest point in the system to get rid of any potential sediment that accumulates. And this pink valve is a float valve placed right at the tank, which will shut off inflow from the source when the tank is full and turn it back on when the tank begins to deplete. This is so that we don't use more water than is necessary and have overflowing in the tank and wastewater. This is a profile view of the trench with an 18-inch minimum, as I said, 24 inches under the road. And we set the minimum base width to 10 inches for construction feasibility so that people can actually reach their hands in there. And once the trenching is complete, this will all be backfilled and compacted to protect the pipe.
And the slow sand filters are located at the base of where the surface water flows over a vertical wall of rocks. So a diversion system is going to be built at that spot, and it will divert water to our two sand filters. There are two boxes for the sand filters individually, and each of them are 5.5 by 5 feet, and together with an estimated average area flow rate of 0.16 gallon per minute per square foot, we estimate that it can meet the 7 gallon per minute flow rate. Along with the two filters, one can be taken offline. It will still give a partial amount of flow rate for the community, so they were slightly oversized. And then here you can see the different layers. We have 2 feet of sand, and we have a foot of gravel, which surrounds the perforated pipe that leads to the tank.
So to chlorinate the water, we have a device that will have a small supply tank dripping into the storage tank right at the inflow of the source. This is the device that we're using. It's actually an IV drip, and it will keep the flow rate constant, and regardless of pressure head in the supply tank, will make sure that the right drip rate is matched. This is our target treated water chlorine concentration. It was set to 0.15, which is between the 0.1 and 0.2 milligram per liter range. And this is a chart showing the device drip rate versus the amount of chlorine that will need to be concentrated in the supply tank, dripping into the storage tank. So as you can see, with the slower drip rates, there would need to be a higher concentration of chlorine in that supply. And with the faster drip rates, there would need to be a lower concentration of chlorine. So we're working with the device, experimenting with it, so that we can provide accurate instructions for the maintenance people at the town, so that they know exactly how much chlorine they're going to need to add to their tank with setting the device. It was donated by Medicine Mondiale. They are a New Zealand company that manufactures these IV drips for underprivileged and underdeveloped communities. And we share some of the goals of community health that are incorporated in our project. This is a schematic of the chlorine supply with the device that will be dripping into this storage tank.
And our total construction cost is a little over $10,000. As you can see, most of our cost is in the material section, which is atypical in the US since labor is so expensive here. But in Honduras, the daily labor rate is $5 per day. So we use that standard daily rate for our labor costs, which came over to just over $1,500.
Oh, sorry. No.
And with every project, there are non-technical issues. The ones we encountered at the beginning were property rights. And we weren't sure if the community would acquire the property rights to where the water tank is held, because the landowner has changed and he has said that he doesn't want people on his land. So that hasn't been completely worked out yet, but it's in the process. We're trying to get a land easement with the landowner. And for our design, we assumed that this land easement would occur since we're using that current water source. The Community Water Board is also slowly increasing a water rate tax per household to 50 lempiras per month, which is about $2.50 in the US. And this price has been deemed affordable by everyone in the community. And the money for this goes to maintaining the system and ensuring that a community member is paid to check the system every week, which part of the reason their system has deteriorated is that they weren't able to have someone constantly maintain it. And education is a crucial component to this project, since if people don't understand the water cycle, water conservation, and hygiene, and how sanitation is related to their drinking water, then the project becomes unsustainable because water's being wasted. People don't understand that mixing dirty water on a clean surface is bad, and things like that. And we have a definition of success for our project. We had these problems of sediment buildup in the pipeline, so we solved that with adding the slow sand filter. Harmful bacteria causing illnesses, we solved that with a chlorination system in combination with the pre-filtration of the slow sand filter. And providing adequate supply to every community member. We have a minimum of 12 psi at every tap, and our hydraulic capacity is able to meet the projected future demand. And this will result in a happy, healthy, and empowered community.
So this is an ongoing project. The community completely understands that a project like this is going to take entire community involvement. As you saw with the Water Board implementing the tax, they're looking at funding this as much as possible on their own. They're looking at hopefully implementing a water project like this in 2015, beginning implementation in 2015, as well as connecting those downstream systems that you saw in the planned use. One of their priorities before implementing a water system is sanitation. They want to incorporate wastewater management and treatment before they go into an overhaul of a potable water system. So we would like to thank the Santa Clara University School of Engineering, as well as the Engineers Without Borders Santa Clara University Student Chapter. We'd like to thank Un Mundo, which is a nonprofit organization stationed in Pital, and they really helped us communicate with the water board, with the community, and find out exactly what their needs were going to be and how we can meet them. We'd also like to thank Medicine Mondiale for donating the IV drip, and as well as our faculty advisor, Professor Stephen Chiesa, without whom this would not have been feasible. So we'd like to open the floor for questions.
So the community looks like it's right on that big river. Did you guys look at using river water and treating that as the source instead of piping it?
So if you use river water, it's a much more contaminated water source, and the cost of treating that water goes sky high, and you have nitrates and things flowing into that river. So it's just not feasible to use river water.
And where was the chlorination system located? I didn't see that one.
It's located right at the storage tank.
It's at the storage tank.
Yeah.
Okay. So what happens if the water somehow gets contaminated between the storage tank and the village with pipe breaks, or the villagers start tapping into the line?
Well, hopefully the water itself will have a high enough concentration of chlorine, a residual chlorine, that it will be able to account for anything.
What's your pressure loss from top to bottom? Because-
Don't know that off the top of our heads.
Did you do a total head calculation? Because you're using relatively
Yeah.
small pipes,
Mhm.
and you've got
They are
a
very
relatively large
Well,
vertical
the drop,
head.
yeah, the drop is huge, but those air vacuum release valves will help us deal with any residual pressures. But as it comes up into the community, it immediately spreads out, and the pressures are